All right, day two, notes for rate laws. The rate law is a mathematical expression that relates the concentration of the reactants to the reaction rate. The rate law is found experimentally, and is based on the slowest step in the reaction mechanism. The given equation, the standard equation for rate law, is going to be this right here. And in here, the brackets indicate concentration, and the x and y each are the order of the reactants. So the x is the order of concentration A, and y is corresponding to B. Okay, K right here is going to be the rate law constant. Okay, and the one rule that you got to remember is that the products do not appear in the rate law. So products do not appear. And another thing to note is that intermediates, 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 and catalysts do not appear in the rate law. Do not appear in rate law. All right. So zero order. The concentration of the reactant does not affect the rate of the production of the product. If the concentration of the reactant is doubled, the production of the product is not affected. Is not affected. First order. The concentration of the reactant does affect the rate of production of the product. If the concentration of the reactant is doubled, the production of the product is also doubled. Is doubled. All right. So, taking a look at the second order now, the concentration of the reactant does affect the rate of the production of the product. If the concentration of the reactant is doubled, the production of the product is going to quadruple. Quadruple. All right. Third order, the concentration of the reactant does affect the rate of the production of the product. If the concentration of the reactant is doubled, the production of the product increases by a factor of 8. Factor of 8. All right. So the overall order is just going to be the sum of all orders. Sum of all orders. The total amount of orders all added up together. The specific rate constant, K, is a proportionally constant, proportionality constant relating the concentration of reactants to the rate of the reaction. A big K means it's going to be a fast reaction. Small k is going to be a slow reaction. Let's take a look at the first example. So here we're given the equation H2 plus 2NO is going to be converted into N2O and H2O. Based on our law that we covered earlier, we know that we have to exclude the products because the rate law only covers reactants. And based on these three experiments, this is experiments 1, 2, and 3, we gotta find the order with respect to NO, hydrogen, and the overall total order. So for NO, if we start out with NO, we have to find the two experiments out of the three where NO changes, but the other hydrogen stays constant. The only possible combination for that is going to be experiment 1 and experiment 2. The NO value changes from 0.3 to 0.6, but the hydrogen value stays constant at 0.35. So how do you set this up? For NO, we're going to grab the highest number. So it's going to be 0.60 over 0.30 to the x equals the corresponding value for these, which is 0.6 corresponds with this number, 1.134. 134 times 10 to the negative 2. And 0.3 corresponds with 2.835 times 10 to the negative 3. And all you do is plug this first parentheses into the calculator, which should give you 2. Carry the x over, and plug this into your calculator, and that should give you 4. We know that x equals 2. So for NO, it is going to be the second order. Second order. All right. So for hydrogen, we have to do the same thing. But this time we're solving not for x, but y, because the rate law is K concentration of A to the x and concentration of B to the y. And we considered the fact that A is going to be NO, so B is naturally H, hydrogen. All right, so for hydrogen, it's going to be the similar process. But now we have to look at the experiments up here on the table, and we got to find one or two of the three where hydrogen changes but NO remains constant. The only possible one for that is going to be experiment 2 and 3. Hydrogen changes from 0.35 to zero point 0.7, but NO remains constant at 0.6. Alright, so for hydrogen, we have to do the same thing, same setup. So 0.70, highest number on top, 0.35, and then this is to the y, equals the corresponding numbers for this. So 0.7 is 2.268 times 10 to the negative 2, and 0.35 corresponds with 1.134 times 10 to the negative 2. Alright, so when you get this, all you got to do is same process as the NO. You plug it into your calculator. So 0.7 divided by 0.35 is going to be 2. Carry the y over. And for this, you got to plug this into your calculator. So 2.268 times 10 to the negative 2 divided by 1.134 times 10 to the negative 2 will give you 2. So now we know, same for this, y equals 1. So this is going to be first order. All right, so we can write our answers here now. Concentration of NO is going to be second order, as stated here. And our hydrogen is going to be first order, as we stated here. All right, and it's asking for the overall order. So overall order is going to be the sum of all the orders. So 2 plus 1 is 3. Third order. That is it. All right, next is asking for the rate law. The rate law formula is looking like rate equals K times concentration of A to the X and concentration of B to the Y. So we already found all the information because this X value is NO and this Y value is H, the order of H and NO respectively. So we can write it rate, I'll write it in a different font or color, rate equals K, the rate law constant, times the concentration of NO, we considered it A, to the X, which is the second order, so an exponent of 2, and the B is going to be hydrogen, H2, and it's first order, so we can put a 1. I always put a 1 to notify that I did, in fact, go through and list all of it. And that is it. So the rate law is that. All right, and we got to find K now. What is K? So this is the rate law constant right there. And all we got to do is take a set of experiments. So say experiment 1, and all we got to do is plug that in. So just make sure that you use the same data points. So if you're using this, stay with this. So don't go around, selecting random things. Always choose the data points related to the experiment. So all you got to do here is take this equation or this rate law here that we figured out, and all we do is calculate it. So the rate is, say we're going to use experiment 1. Rate is 2.835 times 10 to the negative third equals random k times the concentration of NO, zero point 0.3, to the second power, because the rate law order is 2, and the concentration of hydrogen, 0.35, and to the power of 1, because the rate law is the first order. So all we got to do is take 0.3 squared, 0.3 squared, times 0.35 to the power of 1, which is just 0.35. So you're going to get 0.09 times 0 times 0.35. All right, and that is going to be on your k side. So if I write this a little differently, it's going to be 2.835 times 10 to the negative 3 equals, multiply these together, so you're going to get 0.0315 k. So to figure this out, all we do is we divide both sides by 0.0315 divided by 0.0315, and you should get your k value. So when you do this on your calculator, 2.835 times 10 to the negative 3 divided by, what is that? 0.0315, sorry. You should get value of 0.09. And your unit for k is, this is probably the hardest part, is going to be on the format of, here I'll write it in a different color. The format of unit is going to be always in M, in capital M, which is molar, negative question mark, S, which is second, negative 1. So this is going to be, this question mark equals the overall order minus 1, no matter what. So this is how you calculate unit. So m to the negative question mark times s to the negative 1. So our overall order here was the third order. So 3 minus 1 is 2. So our unit is going to be m minus 2, question mark is found using this, and then s negative 1. And that is our answer. That is our k value. All right, let's take a look at example number 2. We're given here the equation, and we are told to ignore the product side based on our rule that we talked about, and it's the same process. All right, so we got to find two sets of experiments for, let's start with NO since it's the first given, um, or sorry, H since this is the first given. We got to find it so that the value of H changes, but the value of NO stays constant. So the only experiment where that works is experiment 2 and 3, where H goes from 0.122 to 0.244, and the NO value stays constant at 0.21. Right. So starting with H, all we do is put this big value on top, 0.244, a small value 0.22 on the bottom, to the X equals, the 0.22 value corresponds with 0.271, and the 0.122 value corresponds with 0.0339. So when you plug this into your calculator, you're going to get 2x, the x carries over from here, and when you plug it into 0.271 divided by 0.0339, you're going to get 7.99. 7.99, which we're going to round to 8. If it's close enough, we always round, so 8. So we know here that x is going to be 3, because 2 to the third power is 8. 2 times 2 times 2 equals 8, right? All right, so this is our third order hydrogen, and we do the same process for NO. So we have to look here and figure out which two experiments we have to deal with in order to find the one that NO changes in value, but H remains in constant, which is experiments 1 and 2. NO moves from 0.42 to 0.21, but H2 stays constant at 0.122. Taking into account that, we're going to take a look at this. Higher number always goes on top, 0.420 all over 0.210 to the y this time equals corresponding values. So 0.42 corresponds with 0.136 here, and the bottom number 0.21 corresponds with 0.0339 right here. All right. So all we do is plug this into our calculator. 0.42 over 0.21 will give us 2y. Y carries down. And 0.136 divided by 0.0339 will give us 4.011, which we're going to just keep at 4. So we take this, and y equals 2. Because 2 to the 2 squared is 4. So we know that NO is going to be the second order. All right, let's write our answers. So concentration of NO, brackets, always brackets, is going to be the second order. The concentration of H2 is going to be the third order. And the overall order which is when we add them all together, is going to be fifth order. 3 plus 2 is 5. Fifth order. And that is it. So using this information, we can write our rate law. Rate law is always rate equals K times concentration of A to the X and concentration of B to the Y. So taken into account here, we set hydrogen as A. So rate equals K concentration of H, and we know that we found out the concentration order is 3, and the concentration of NO, the order here is 2. So that is your final answer here, and that is it. For C, all we do is plug in a set of experiments from the table into our given or created rate law here. So I always like to use experiment 1. So all you do is take those numbers and plug them in. Just make sure you gotta use the same values on experiment 1 and not going around using random values. Always from the same experiment. Our equation here is rate equals K times concentration of H2 to the 3 times concentration of NO to the 2. So finding this out, we use rate 0.136 on experiment 1 equals K times concentration of H, 0.122 to the third power, times the NO value, 0.42 to the second power. And all you do is take 0.122 to the third power right here, and multiply that by whatever you get based on 0.42 to the second power. So you're going to get 0.001815 for the first here, and 0.1764 for here. So let's write that down. And 0.001815 848. So multiply these two numbers together, and you're going to get a very small number, which you're going to keep. And all you're going to do is get that number and divide this. So 0 point in your calculator, 0.136 divided by whatever you just multiplied together with these here. So this value here. And you're going to get k equals 424.58. And your unit is the cheating method that I taught you here was this. So the overall order is fifth order. So it's going to be 5 minus 1 is 4. So m to the negative 4, and then s to the negative 1 is always constant. So that is your k value, the rate law constant. All right. So let us cover other notes now. All right. So reaction mechanism and the rate determining steps. Reaction mechanisms are how reactions progress from start to finish. A balanced equation does not tell you how a reaction occurred. An elementary reaction is a reaction in which reactants are converted to products in a single step. So, for example, the M and N are moles in the balanced equation here. So this plus this is going to be C. That would be an elementary reaction. And for elementary reactions, we can take the number of moles. M corresponds with A and N corresponds with B. So these will become the X and Y. So they will correspond to the exponents, the orders in the rate law. And this is for single step reactions only because the balanced equation can be used to determine the rate law. Most chemical reactions, however, consist of two or more elementary reactions. So this trick here only works with elementary reactions that are just one step, single steps. The reaction mechanism for multi-step reactions. Most reactions are not single step but require a series of steps. We call this the reaction mechanism. So these are the series of equations and reactions that we see in order to get the final product from the reactants you started with. The reaction mechanism can be used to determine the rate law if the slow or rate determining step is shown. So the slow rate is going to be always the rate determining step. We always base our rate laws off the slowest step because it cannot go faster than the slowest step. We see the overall net change when we balance equations, but in most cases it is a series of reactions taking place. The reaction mechanism must agree with the experimentally determined rate law if the rate law is known. So taking a look at this graph here, we can see here there is the highest curve here, highest point right there, which is going to be our activated complex. And each of these small little things here are going to be intermediates. Each peak represents an elementary reaction, and each valley is an intermediate. So the intermediates are here, and the elementary reactions are up top, right? Sorry, up top, right there. All right. So the rate determining step says that a reaction can never proceed faster than its slowest step. It can never be faster than its slowest step. Intermediates are substances that are produced by one reaction and later consumed by another reaction. So we have to note here that intermediates are going to be starting as products but end with or end as a reactant. Catalysts are substances that start a reaction and later produced by another reaction. So in the end you're just going to have a catalyst. So for these, it starts as a reactant and ends as a product. as product. So these are the ways you determine whether something is an intermediate or a catalyst. And that is something you might want to remember. So, right there. All right, let's take a look at an example. All right. So we have here two equations. So the um, series of steps here, the reaction mechanism. We're given that this one's slow and this one's fast. So we know that this one is going to be clearly more important. All right. So we got to take a look at both of these equations and we got to see which ones we can cancel out if applicable. Just like Hess's law from thermochemistry, we know that whatever's on one side and the other side cancels out. So when we take a look at this, N2O is on the reactant side, same for here. N2Os are both on the reactant side. The O, one's on the reactant side and one's on the product side, so we can go ahead and cancel that out. And the rest of these are on the product side and they do not cancel. So we know that oxygen was canceled, and we can go ahead and answer this question here. What are the intermediates? And as we've talked about in the previous notes right there, the intermediates are starting as a product but ending as a reactant. So I'll just write that. Start as product, end as reactants. So we started oxygen here that canceled off, started as a product, but ended as a reactant because the slow moves to fast. We know that this equation is reaction is going to be this moving on downwards. So if oxygen started as a product and ended as a reactant, then we know that oxygen, or I'll write it in a different color, oxygen is going to be an intermediate. All right. What is the overall balanced equation? We just canceled everything out that we can, so we can write this balanced equation. So all we do for this is combine all remaining um, compounds. So we can write this. We'll start with the reactant side. We have two N2Os, two N2O, which converts into we have two N2s, two N2 plus we have O2, O2, and you can either put a 1 here or don't. It is up to you. All right. So what is the rate law for this reaction? And rate law we write based on the slowest step. Write based on slowest step. And so the order numbers, the x and y's from the rate law, the base rate law equation, is going to be coefficients. Coefficients are order numbers. Numbers. All right. So with this information, we can go ahead and write the rate law. So we are not going to be writing a rate law based on this because that's the balanced equation, not the slowest. We always write it based on our slowest. So we can go ahead and exclude the products because our rule says we only involve the reactants. So rate equals rate constant K, the concentration of N2O, and since there is no number in front of the N2O, we take that as an indivisible 1, so our order number is going to be 1. That is our rate law. That is the rate law. That is it for our unit notes.